Hello students, welcome back. Let's go back to section 3, Fulmer's method, and let's work on some concrete problems. First, an easy problem. Easy I mean by just 2 by 2, so the previous method, the Laplace inversion method, works just fine because it's not too difficult to find out the inverse matrix. Nonetheless, we'll try it with Fulmer's method this time. So how does it work? First, we have to find out the SI minus A. No, actually no. Let's go directly to the characteristic polynomial. Characteristic equation, if you may. So, okay, how do you do that? That is, we have to calculate SI minus A, this matrix. And that is this is SI minus A, and A is given like this. So this is S minus 2, and then 0 minus 1, 0 minus of negative 4, so we have plus 4, and S minus 6, and there goes my matrix Si minus A. And the characteristic polynomial is the determinant of this. You see, resolvent matrix is the inverse of it, but that's difficult to find out. Well, in this case, it's not too bad, but just find out the determinant. Okay, determinant of that, and the determinant of this. So, AD minus BC, so crisscross, S minus 2, S minus 6, minus the other two, minus 4, so minus plus 4. So what is this? Let's simplify. I'm going to get S squared minus 8S plus 12. Yeah, sum them up. Okay, and then plus 4. Total, I'm going to get plus 16. Okay, I have it. S minus 4. Total quantity squared. And what we have a double root. So we have only one zero, double zero. So if I set this characteristic polynomial equals to 0, so we have double root. So I'm gonna get this eigenfunction. Are you with me here? In the previous example that I used as a motivating example over there, I had two different eigenvalues. So we had two different eigenfunctions, e to the negative t and e to the positive t. Here, in this example we are doing now, I have a double root. So e to the 4t and then t times that. Okay, so what do I expect? This is gonna be matrix M1 times e to the 4t power, matrix M2 times t e to the 4t power. That's what I expect. That's what I get from this characteristic polynomial business, or you can name it differently, characteristic equation or eigenvalue or whatever you name it. That's step 1. Okay, step 2. let's determine the coefficient matrices, M1 and M2. Okay, here we go. We have one equation here. And then let's take the derivative. And let's take the derivative of this for M1 e to the 4t power. Is that clear? And then this one is going to be a bit harder because we need a product rule here. So we need M2 e to the 4t power. And then we have to take the derivative of the second terms for M2 t e to the 4t power. Let's see, did I do everything correctly? Derivative and then the product rule. So derivative. I don't need second derivative because this is just 2 by 2. We need two equations, so original and first derivative will do. Alright, we got these, so plug in t equals to 0. Plug in t equals 0, what do you get? This is 0, so this whole thing is a 0 matrix. E to the 0 power, what is it? What is e to the 0 power? Identity matrix I. Okay, that was simple. E to the 0 power, that's 1, so that's gone. E to the 0 power, that's 1, but this is 0, so it's all going out. You know, this is 0. Okay, alright. Next, I'm plugging in t equal to 0 to this guy, so that's 0, so we have e to the 0 power. Again, this is identity matrix I, so times something, it stays the same. Next, plug in t equal to 0, so that's 1, so it goes away. And that's 1, so it goes away, t equals to 0, e to the 0 power. And as for this is 0, so it all goes away, and this is what we get. Looks like we have this system of linear equations. Okay, M1 is equals to I, so I get M2 is A minus 4 M1, isn't it? But this is equal to I. Okay, looks like I got that. Not too bad, not bad at all. Okay, so M1 is equal to I, so 1, 0, 0, 1, all right. M2 is A minus 4I, so here's my A. Minus 4 times I. But then again, 4 times I can slip these in. And then what is this? 2 minus 4, I'm getting negative 2. 1 minus 0. And negative 4 minus 0. 6 minus 2. Looks like this is what I'm getting. Did I do my computation correctly? Okay. Here's the conclusion. So this matrix times e to the 4t power plus this matrix times t times e to the 4t power. Looks like that's complete. This is perfectly okay. But in case if you want to simplify a little bit further into a single matrix, you can do something like this. E to the 4t power comes from here, and then minus 2t exponential 4t. Okay, that was 1 entry. 1 2 entry, I don't have anything here, that's 0. And this is going to be 1, so t e to the 4t power. Here, I have nothing here, 0, so we have negative 4t e to the 4t power. And finally here, e to the 4t power plus 2t e to the 4t power. Looks like this is a little bit more simplified version or one matrix version, but this is perfectly fine. That's the computation I have. Let's see, can I put everything into the same viewing window? Okay, barely, but I got it in. How does it look? Characteristic polynomial. Si minus a is straightforward, and then take the determinant instead of taking the inverse, because inverse matrix is expected to be complicated for higher dimensions, so have a practice here. Just take the determinant, and then that is the characteristic polynomial. So from here, progress pretty much the same way as you have been doing from chapter 4, or even before that. Set it equal to 0, characteristic equation, and solve it. We get eigenvalues, and then based upon those eigenvalues, you're gonna get the basis functions or eigenfunctions. And then we get the linear combination of those basis functions or eigenfunctions. But then again, we are talking about matrix functions this time, so coefficients are not scalars, but coefficients are matrices. So coefficient matrix M1 and coefficient matrix M2, we have to find those out. How do you do that? We need a system of linear equations. We have two unknowns, two matrices to determine, so we need two equations. Plug in t equals to 0, that's giving you 1. The other, you can get it by taking the derivative and plugging t equals to 0. Simplify, we get that. And then further computation, and then just plugging in. That's a solution. Now here in my notebook, I have a little bit fancy version of the same thing using those the BQ and EQ, those kind of things. Now, if you remember those kind of things, actually that's great because that really saves us some space. So characteristic polynomial here is the same thing we did before. And from here, I get the zeros of the characteristic polynomial, that's just 4. So EQ, which is the standard basis for the proper rational expressions given by something over s minus 4 to the quantity squared. If I decompose by partial fractions, I'm going to get 1 over s minus 4 and 1 over s minus 4 squared. And then BQ, those standard basis functions associated to these two by taking a Laplace inversion will be e to the 4t, t times e to the 4t. And then we get exponential, matrix exponential can be written as the linear combination of these two basis functions, BQ. And then, well, we have this M1 and M2 like this. So first step can be written in a little bit more elegant fashion. and then I can save some space if you use these a little bit fancy notations. But only if you remember all those EQ, BQ, all those businesses. But I left all those in chapter 4 as optional topics, to tell the truth, because it goes a bit too deeply into linear algebra, so it may not be for everybody. Solving the system, not too bad, same thing, plug in t equal to 0 after taking the derivative or before, and then in the end we get the conclusion, same computation as before. Okay, let's stop here, and we're going to meet again for the next problem in a fresh new video here. That's going to be harder because we are dealing with 3 by 3 matrix this time.